But before I show you an actual phase diagram, I want to just take a moment and try to explain to you how this can be. And we're going to do this by just drawing little pictures and just thinking to ourselves, how could you imagine packing fats together? So remember I told you that triglycerides, and this is really a general fact for all fats, but triglycerides actually consist of these two arms with this one long arm that's stuck to it. And if we start to think to ourselves, just draw on a little doodle pad, how is it that we're going to stack these things together? There are really at least two ways that you can do it. So one is that what you could imagine doing is taking the long arm and stacking it in such a way, like it's shown in this picture, where the long arm is actually, that is, the single arm is actually adjacent to the double arms in the layer before it. So this picture is what's called a double chain packing. What you see is that the long arm is on, of one molecule is on top of the double arm on the other, and they basically flip back and forth from layer to layer, which gives rise to the packing. So there's also another logical possibility, which is what people call the triple chain packing, in which what you do is you put the two double arms on top of each other and you put the single arms on top of each other. So you basically align the things so that the single arms are like this and the double arms are like this. That's shown in this picture. And when you do that, that's called the triple chain packing, and that's a different way of packing, right, the triglycerides. Now, these two different packings, have different energies, right? It might be more sticky to do double chain or more sticky to do triple chain. And whether it is what is true actually really depends on the detail of the fats. I mean, so for example, if you could just imagine as a thought experiment, if you had a saturated fat in the single chain, then the saturated fats might like, the single chains might like to stack together very well, right? Whereas if the unsaturated fats were in the chains, then they're sort of harder to stick. And then of course, the heads with the two double chains, that could be a different stacking interaction altogether. And it really, as you can see from listening to me, it gets a bit complicated to figure out just from thinking about it alone what the different stacking behavior is. And this is really something which is an experimental subject. It can be empirically determined by studying the phases of fats and by looking under the microscope, under a very powerful microscope, to find out, how the molecules are stacked. Okay, so with that as background, I now want to show you the phase diagram of chocolate, and I'm going to try to relate this to what I just said. So this is the phase diagram of chocolate. So chocolate has, as I said, 6 crystalline phases that vary in temperature from 18 degrees to 36 degrees. So the lowest phase, which people call phase 1, cleverly, has a melting temperature of about 18 degrees. The second phase, which people call phase 2, is about 22 degrees. And then there are other phases. There's phase 4, which is 34 degrees, and phase 6, which is 36 degrees, and so on and so forth. And these are the 6 different phases. So what do I mean by different phase? What I mean is, well, for one thing, it melts at a different temperature. It just, comes apart. If you made the material out of only that phase and you heated it up to the melting temperature, then it would come apart at that temperature. So, and I also mean that if you were to look at the structure, that is the way the molecules are packed, they're actually different in each of these different phases, which is the reason that it melts, right, at different positions. Now, what's interesting about these numbers, if you just think about my little experiment with my piece of chocolate a little while ago, is that if you remember that body temperature, right, that is your mouth is 37 degrees and your hand is, let's say it's 28 degrees or something, if you want to find a material out of this phase diagram which doesn't melt in your hand but melts in your mouth, you can see really the only options you've got, even from the get-go, are phases 5 and 6, the two highest phases. Maybe phase 4, it's close to the borderline, but phases 5 and 6 are really what you have. And in fact, it turns out that 5 and 6 are the ones that, and in particular phase 5, is the phase that you need to hit in order to make the chocolate that you know and love, and that we saw so spectacularly illustrated by Enrique. Now, if you think about preparations, you can immediately see from just looking at this diagram and thinking about how it is you're ever going to do this, why it is so hard for the home chef or for somebody who's inexperienced like me to make chocolate in their kitchen. It's because you somehow have to basically get the cocoa butter, which, you can buy cocoa butter, or you can just take chocolate and melt it, like, put it at very high temperatures, and you will basically get for yourself a mix of cocoa butter. But then the question is how do you get it to only crystallize in the phase at phase 5, which is what you want? I mean, clearly, if you cool it to a low temperature like 22 degrees, then it can cool into all of these different phases. So what are you supposed to do to make this happen? And the complexities of making chocolate are all associated with this issue.